Hello out there, dear friends, and welcome once more to another video in our YouTube channel. In this video, friends, we shall be looking at the correction of the A-level GCE organic chemistry. We shall be looking at the June 2023 of paper 2, guys. It's A-level chemistry. So friends, stay tuned and please watch the video from start to finish, guys, because at the end of this video you shall be able to walk into that exam hall and give those examiners the marking guide as far as organic chemistry is concerned. So friends, I already uploaded the one for physical and inorganic chemistry. So friends, if you've not watched it, I highly encourage all of you to go and watch it, because it is so important and it's going to help you a lot in your exams. Great. So friends, for a quick reminder, if you're new to this channel, don't forget to hit that subscribe button looking at you and press the bell icon to always get notified each time we upload new videos. Keep in mind that as soon as the GCE finishes, guys, we are going to be looking at the various exams of the various concours, because most of you guys will be writing concours to enter vocational schools. We shall be looking at those exams as well. Great. So friends, good luck to all of those who will be taking chemistry today. And the truth be told, guys, I'm very sorry that this solution is coming very late. Okay, it's coming very late, but if you take your time and watch all the video, you have no problem. Great. So friends, let's get started. So friends, as you can see, the first question on screen is saying that an organic compound X contains 54.9% carbon, 10.9% hydrogen, and 13.9% nitrogen. So friends, these are the percentage compositions by mass. Okay, then now they are saying that a molecular weight determination of the compound gave a value of 230. Great. So this is the relative molecular mass of the compound. Then the Roman 1, they are saying that calculate the empirical formula of the compound. Roman 2, we should determine the molecular formula of the compound. Then the Roman 3 suggests the structural formula of the compound X, given that it gives butylamine when warmed with bromine and a concentrated potassium hydroxide. Then the Roman 4, how can I identify the presence of nitrogen in the compound? Great. So friends, let's just get started. Friends, we should know that the total relative abundance of the compound, because each time the relative abundances have been given in percentage formats, we must have to sum all of them to see that it is 100%. Okay, we have to sum up all of them. So if you sum up all their relative abundances, guys, we will see that it is 79.9%. okay, it is not 100%, as you can see, it is not 100%. So that's to tell us that there is a certain percentage of oxygen in this compound. Okay, there is some percentage of oxygen in this compound, though the question did not tell us, but since you sum up all the relative abundances and it is not equal to 100%, it is rather 79.7%. so the other fraction is for oxygen. Great. So friends, as you can see, to get that for oxygen, now we simply take 100 now and we'll subtract it by the percentage we subtract it by the sum of all the percentages as we have here. So if we do that so well, guys, we are going to have an answer of 20.3%. so this is now the percentage by mass of oxygen. Good. So friends, we are now set to calculate our empirical formula and hence our molecular formula. So we are going to put all the various elements like this. We have carbon, we have hydrogen, we have nitrogen, and we have oxygen. Good. So friends, now we are going to insert their various percentage compositions by mass. Carbon is 54.9, hydrogen is 10.9, nitrogen, as we see, is 13.9, and oxygen is 20.3. Good. So friends, secondly, what do we do now? We are going to divide each of these our percentage compositions by mass by their respective molar masses. Okay, by their respective masses. So the mass for carbon, guys, as you all know, is what is 12, right? Good. That for hydrogen is simply 1, so we divide the 10.9 by 1, dividing 54.9 by 12. We have this. Then nitrogen is 17, guys. Is 14, sorry. So we are going to have 13.9 divided by 14. Then for oxygen is 16. So we are simply going to have 20.3 and we divided by 16. Good. So friends, if we punch this our values now, we are going to have that for carbon, we have 4.575. So friends, I will highly plead on all of you, okay, I'll highly recommend all of you to always give your answers to at least 3 decimal places. Okay, at least 3 decimal places, because sometimes too much of approximations are going to give you inaccuracy in your results. Okay, so in the exam, no matter the decimal places in which the equation has given you, always try to put it to at least 3 decimal places at least. Good. So we have 4.57 where we divide, then dividing 10.9 by 1, we simply have our 10.9. then dividing 13.9 by 14, we have 0.9929. so this is to 4 decimal place. If you want to put 2 decimal places, good, this is going to be 0.993. then that for oxygen, guys, we are simply going to have our 1.2688. good. So friends, these values we have here are the mole ratios. Okay, are the moles, sorry. Okay, these values we have here are the moles, because we simply took the masses that we had, right? Their percentage by masses, and we divided by what the mass of the various elements. Good. So friends, now these are the moles of the various elements, right? We now have to get the mole ratio. By so doing, we are going to divide each and every one of them by the smallest, and the smallest in this case is 0.9929. so by so doing, guys, dividing 4.575 by 0.99, we are going to have our answer to be approximately 5. Do that for 10.9, guys, we are going to have our answer to be 11. Do that for itself, that's dividing 0.9929 by itself, we simply have 1. And also dividing for 1.2688, we also have approximately 1. Good. So friends, these are the ratios that we have. Okay, these are the mole ratios. We have 5:10:1:1. So we can conclude that our empirical formula now is now going to be C, this C, which has 5. We have here C5, H11, then we have N1, then we have O1. Good. So this is what we have, guys. This is our empirical formula. Good. So friends, I hope you understood how to get it. And friends, I'll plead on you on one thing, guys. I'll plead on you on one thing, friends. If you subscribe to the channel already, thank you so much, and please share the video with your friends. And most importantly, friends, I'll plead with you people solemnly, guys, please just press the like button beneath the video. If you've not liked the video, friends, please make sure you like the video by clicking the like button. That goes a long way to motivate me to keep producing more great content for you. And don't forget to leave your comments in the comment section down below if there's something you had difficulties in and you want more explanations, and I'm going to do so for you guys very fast, guys. Thank you so much. Then friends, now since we have the empirical formula, now let's move on to get the molecular formula. Great. But we should first know that the molecular formula is simply given as the empirical formula times n. Okay, the empirical formula times n. We have the empirical formula already, but we don't have n. Okay, we don't have n. But we should also know that this our n is given as, that is the total relative molecular mass of our compound that has been given to what, 230, all over the relative molecular mass of our compound X, of the empirical formula of X. Yes, that's the interpretation of this. Okay, we've used X because the question here was talking about X. Good. Then now, guys, if we look for the relative molecular mass of this empirical formula by taking 5 times the mass of carbon, keep in mind that the mass of carbon we have here to be what, guys, to be 12. That's 5 times 12 plus mass of hydrogen is 1 plus 11 times 1 plus that of nitrogen is 14 times 1 plus that of oxygen is 16. Summing up all those values, guys, we are still going to have our answer to be 115. So now dividing 230 by 115, guys, we have answer to be 2. Good. So this is the value of n. So our molecular formula now can translate into we have C5H11NO. This is the empirical formula now times the value of n as we have it here. We have our n to be 2. Good. So friends, this is our molecular formula. You can multiply everything by 2 to have C10H22N2O2. It is up to you. Okay, it's up to you, but I think it's okay like this. It's okay. It's perfectly okay like this, friends. So friends, please don't forget to like the video. It goes a long way to motivate me, friends. I highly plead on all of you to please like the video by just pressing the like button. Thank you very much, friends, and please share it out with your friends. Share it out, because just this video itself can change their grade for good. Okay, thank you so much, guys. Thank you so much. Now friends, the next part wants us to the next part, friends, is saying that suggests a structural formula of X given that it gives butylamine when warmed with bromine and concentrated potassium hydroxide. Great. So friends, what we should know is that when X reacts in the presence of warmed bromine and potassium hydroxide, it means that X has undergone the Hofmann's degradation, okay, and hence X is an amine. So friends, this is what is so particular, because they said X has given us what? Butylamine, right? X has given us butylamine. And friends, please keep in mind solemnly that keep in mind what the question has said, okay? Because the question has talked about bromine and what? Concentrated potassium hydroxide. Right? Each time you see these two guys, what should come to your mind must be the Hofmann's degradation. Hofmann's degradation. And the Hofmann's degradation, guys, is simply a reduction reaction wherefore the number of carbon atoms are being reduced by 1. And it only takes place for amides, okay? For amides, like to convert from an amide and arrive at an amine, you have to use the Hofmann's degradation. So now in such a case, now if we use the Hofmann degradation on this, because the question told us that by so doing it gave us what? It gave us butylamine, right? That means the number of carbon atoms they have been reduced. So the initial carbon atom that we should have now should be what? 5, and this is what we have here, 5. So by using this C5H11, that it has given us butylamine, therefore means the number of carbon atoms have been reduced. Good. So friends, keep in mind that this our compound we have here is simply a dimer, okay? It's simply a dimer, and the compound itself, the homologous series, guys, in fact is a derivative of carboxylic acid, okay? It's an amide, so it's a derivative of a carboxylic acid, so it's an amide. So friends, now to draw the structure of this guy, we are since, and friends, you might also be asking me that what is a dimer. So friends, what you should know about a dimer is that it is formed between, most of the times you have two identical molecules in which the atomic mass, or in which the relative molecular mass of that molecule doubles, okay? Because if I ask you to get the relative molecular mass of this compound, right, all you need to do is just to get the relative molecular mass of this compound we have here, multiply that by 2. Great, multiply that by 2. So guys, that's how it is. Then friends, to give the structure of this compound, guys, since we know that it's a dimer already, the reason for doing so is that we have been told that it gave butylamine when warmed with bromine and potassium hydroxide, right? That's concentrated, and it gave us butylamine, means that's gone through the Hofmann's degradation. Nobody will tell you that it is Hofmann's degradation, okay? Nobody will tell you. You're the one to look at the reagents, reaction conditions, and the kind of organic compound and detect it. Good. Okay, so friends, in that case, let's see how we can bring forth the structure. We know that it is simply going to be this guy twice, right? How are we going to draw it now? That's what matters. So we have been told that it contains what? A carboxylic functional group, right? We were told that it contains okay, nitrogen, oxygen, carbon, and alright, I think that's all, friends. Great. So we are simply going to have it, since we know that it's an amide, right? It's an amide, which is a derivative of a carboxylic acid. It's an amide, guys. So after having this, now we expect to have the amino group. This is the amino group, friends. That's what we have. Then now, since it's a dimer, now this compound has to link with an identical compound of itself. Then now we are going to have this oxygen linking with this amine. Friends, don't make the mistake of taking oxygen to link with another oxygen. It's not proper. Good. You'll mark it wrong, friends. Then now you also have this guy now linking with this oxygen, friends. So this is the structure of this compound, okay? This is the structure. This is it, as you can see. Like I said, one mistake that students are going to make is that they're going to link oxygen to oxygen, amine to amine. Good, friends, that's not correct. That's wrong. And the common mistake that students are going to do is by just leaving this question unanswered. Great, they'll leave it unanswered. Yeah. So friends, try to get the clue from the question, okay? Because the clue to this question is simply by saying that this our compound has given what? Has given butylamine when warmed with bromine and potassium hydroxide. Great. So you should know that it has simply passed through the Hofmann's degradation. And in Hofmann's degradation, one carbon atom gets reduced, and it takes place only between amides, and it gives you the corresponding amine with one carbon less than the corresponding amide you used initially. Great. So friends, I think that was understood. If there's something that is not understood, friends, make sure you put it in the comment section down below, friends, and I'm going to reply to it as soon as possible. Thank you very much, guys, and please like the video. It goes a long way to motivate me. So let's move on to the next question, guys. We can see on screen it's saying that an organic compound with molecular formula C4H9O2N has both the amino and the carboxylic acid functional group and is optically active. Great. So friends, take note of all the data that the question has provided. Now they are simply the Roman 1 is saying that what is a functional group, then the Roman 2 give the conditions for the compound to be optically active, then Roman 3 give the optical isomers of the compound. Great. So friends, let's tackle these two and we shall look at those ones later. Alright, now friends, we should know that a functional group, guys, is simply a group of atoms, a group of an atom, a group of atoms, or a bond, guys, which is present in an organic compound that determines the chemical behavior of that compound. Okay, it's super important, guys, super important. It's simply a group of atoms or a group of atom or a bond present in an organic compound which determines the chemical behavior of that compound. You could still say in a different version that a functional group is simply an atom, group of atom, guys, or a bond present in an organic compound which determines the chemical reactivity or the behavior of that compound. Great. Super important, guys, very important. Then now the Roman 2 is saying that they should give the conditions for the compound above to be optically active. Great. So friends, we know that for a compound to be optically active, guys, this our compound, guys, must have what? Must have a carbon atom linked to 4 different groups. In bracket, guys, the compound should have a chiral carbon atom or a chiral center. Great. So friends, for a compound to be optically active, like you can see here, it should have, first of all, guys, a chiral center. A chiral center is simply a carbon atom in which there is no line of symmetry. Okay, or better, a carbon atom that is linked by 4 different groups. Keep in mind, friends, I didn't say functional groups. I didn't say so. I said groups. Okay, I said groups, not functional groups. Not functional groups, guys. Take note. So that's it. The next part wants us to give the optically active isomers. Alright, so friends, let's now have the first guy. They said the compound was C4H9O2, and so we must exhaust all of those elements you see there. Then we have one of the hydrogens there. Then, guys, we have the carboxylic acid functional group as we have here. Then now the next one that we must insert now is the mirror element. Good. This is actually the point where there is no line of symmetry drawn. Good. Awesome, guys, awesome. So this is the compound that we have, but you have been told it's optically active, so it has a corresponding optically active isomer. Good. But we must have to insert our mirror line to show that that both of them are identical. Great. Okay, because we are going to draw the other in such a way that it is going to be almost the exact opposite of this one. Great, almost exact opposite. So we are going to have it as we have here in this form. It's just like we can reflect it. Okay, we can reflect it, but in this case, guys, we are going to have what we have here. Then that's the carboxylic acid functional group. Then now down, guys, you should know that all of these guys have been reversed. Okay, they've been reversed. Okay, it's just like if you try to fold this one, it is going to fall exactly on this other, right? Good. Yes. So when in such a case, now we are now going to have what we have here. We have our main group. Great. So friends, that's how you can draw the enantiomers. That's how you can draw the optically active isomers, or sometimes you can call it enantiomers. Wait. So friends, the next question is saying that 1,2 dimethyl bromoethane, we have it here, reacts with aqueous sodium hydroxide under reflux. Good. So friends, I would like to draw one attention. You guys should always be mindful of to make sure that the examiner does not to make sure that the mistake that is made by the examiner should not discourage you from answering the equation. Okay, be very careful, friends. Very careful. Then friends, they said give an equation for the reaction. Then the Roman 2, what type of mechanism is illustrated by the reaction? Should write out the mechanism. Then give the product of the following reactions of phenylamine. We have this, that. Alright. So for now, let's take it bit by bit. Let's start from the first. We should give the optic. Now we've done that. They want us now to give an equation for the reaction between this compound and sodium hydroxide. Alright. So friends, we are simply going to have the compound that we have here, which reacts with sodium hydroxide. Friends, keep in mind that what actually reacts is what actually happens is that there is a displacement reaction that occurs. This OH on this sodium hydroxide now is going to displace the bromine as we have here. So we are now going to have now about CH3 all that times 3. Then we have COH plus the bromine now comes and reacts with the sodium we have here. We have sodium bromide. Great. Awesome, friends. Excellent. So that's what we have. So friends, please don't forget to like the video, subscribe to the channel if you've not done so, if you want to have all the latest updates about the exam and there's the GCE, the exam, you have concourse and so on and so forth, guys. All you need to do is just subscribe to this channel and join the others. Thank you very much, guys, and don't forget to like the video, friends. Please like the video, it goes a long way to motivate me to keep producing more content. Great. Then friends, the next part is saying that we should give an equation for the reaction that has already been given. Then they said write out the mechanism. They're asking us the kind of mechanism illustrated by this compound. Friends, as we all know, since this halogenoalkane, guys, it's a primary halogenoalkane, it is going to obviously undergo the SN1 mechanism. Okay, it's the SN1 mechanism. Why SN1 mechanism is so because this our compound that we have here is a tertiary halogenoalkane, and in the process of the reaction, guys, a carbocation is being formed. Which is highly stable. Keep in mind that carbocations formed by primary halogenal compounds are highly unstable. Those for secondary are more stable than alcohols. Then those for tertiary are the strongest and the stable and the most stable. Wait. So friends, the mechanism is SN2. Oops, we are supposed to add reflux. Good. So the mechanism, guys, is an SN. Oh my God, I'm sorry, friends. It's an SN1 mechanism. Okay, SN1 mechanism. Why S1 mechanism, guys? It is so because in the rate determining step, guys, only one of these atomic species is present. Only this our CH3 all the times 3. We have C plus is present. Okay, that is the rate determining step. If it was a primary halogenal compound, like I said, it is going to undergo an SN2 mechanism because it actually prevents a carbocation from forming since it is highly unstable, right? It simply functions in preventing it prevents the atomic species to blend. Okay, so friends, the next part now is asking us to write out the mechanism. All right, so friends, this is what we have. We are going to have this is reacting to give us this our compound, right? Good. And we should know that from here now, from here, this is just simply this compound I repeat. This is just simply the equation I repeated. This is just it. Then from here now, friends, you should know that first of all, the bond between bromine and this our compound is going to break, such that ions are going to be released. Okay, ions get released. Then now we are now going to have our plus Br minus. Then we have OH. Now, friends, you might be asking me where the sodium has gone to. What I have done is that I have simply included just the active part we need, okay, which is the OH minus. Good. So yes, now guys, you see that this guy now is going to combine with this C plus, right? It's going to combine with that C plus, as you can see, combine with the C plus now, and we are going to have our compound here as we have. Great. So friends, that is it. That is what we need. That is exactly what we need. Great. Then friends, let's look at the next part. The next part is saying that we should give the products that have been formed when this compound reacts with sodium hydroxide, when this also reacts with that. Okay, so friend, this is a ketone, right? It's a ketone, a methyl ketone for that matter. So we expect to see an iodoform test which is being formed between this guy, but we lack iodine, right? But we are still going to do it. Good. So friends, let's start with the first case. In the first case where we have sodium hydroxide, this is what we are going to have. Friends, know that the initial equation used by the Kekulé structure of benzene, right? This is the structure in which it used, but I've seen to use the ring. In the exam, make sure you use what has been given. Great. So now we are now going to have it. Now when it reacts with this guy, now we are definitely just going to see oxygen atom upwards. Then we are now going to have ONA. Okay, this, because friends, keep in mind solemnly that we ought to have had iodine such that we could produce the iodoform. Okay, we ought to have it. We ought to have had it. The equation does not give it. Don't bother. Okay, just answer what the equation has given you. Just answer. It is so cool. Wait. So friends, like I said initially, good luck to all those who are taking their exams. Best of luck to all of you as you write. You all shall have all the A grades. Those who have subscribed to my channel and have been watching me for the time now, they have nothing to worry, because they have all it takes to score the A grade. Great. So friends, now this is what we are going to have when this compound reacts with sodium hydroxide. Then now friends, let's look at what happens when it reacts with 2,4-dinitrophenyl hydrazine. So as compound, guys, I'm sure the equation provided the compound, but I won't give it here. I'll just give you for what is being formed. So that is actually the hydrazine. That's a section of it. Then in front of this nitrogen, we are supposed to have a hydrogen there. So it has gone. Now, friends, we are now going to have it now being reacting with this guy. What happens is that it targets by the ring. Okay, it targets the ring of this compound. So this oxygen now is now going to disappear. They were now going to have this our guy like that. Keep in mind, friends, initially that there is an intersection. I mean, there's a carbon atom there. Yes, very important. Where you see carbon, where you see these strokes sticking, means there's a carbon atom in between these two guys. Great. So in such a case now, friends, we are now going to have it as we have. I'm trying to all the arrows intersect. We have that now, friends. Oh, this was a double arrow. Then now we now have this our structure itself. We have so this is what we have, friends. Oops, friends, the benzene ring has been omitted, but don't bother, I'll fix it later. Okay, this one also, the benzene ring has been omitted. So now, friends, to get the compound form when this our compound here now reacts with hydrogen cyanide, guys, all we need to do is we are simply going to take the similar case where we have here. Then now we are going to have the OH minus here. We have OH minus, but since it has attached the benzene ring, we just have it as OH. Then now these are other strips that combines. We have the CH3, because the hydrogen from the hydrogen cyanide is simply going to combine with this lone oxygen here to give us the OH, as you can see here. Then the bond gets broken. We have CH3. Then down now has to be the nitric group. Good. That's it. So friends, let's just see if we can fix these two things. Let's see if we can fix them. Good. Awesome. Great. I'm so grateful. Very, very good. Everything is set now, friends. It's set now. So friends, I hope you understood If you didn't understand, guys, please leave your comment in the comment section down below, and I'm going to reply to it as soon as possible. Let's move on to the next question, friends. Great. So friends, as you can see, the question is in that the following diagrams show the following relationships between the molecules and some compounds. This is what we have been given. Then they are saying that we should give the name and write the structural formula for the isomer of W. The Roman to which of these isomers in A Roman 1 corresponds to W. Identify the compound X, Y, and Z. So we'll come to that, guys. Let's just start. So friends, how do you write the structural formula of the isomer of W? Always you start by giving the name of it. So friends, as you all know, to be able to detect what is this compound, guys, all we are going to do is that we are simply going to look at the reaction of this guy, okay? Because I can see that it has given a positive iodoform test, right? Good. So I'm suspecting that it is either a melty ketone, either ethanol, or a secondary alcohol. Good. Great. So those are the possibilities in which we have, right? But in this case, that's given an iodoform test, and not just that, guys, it has been reduced from it has left from where, guys? It has left from this guy to where? To C3H6, and this is a ketone, and we know that only secondary alcohols can be oxidized to ketones, right? Good. So this must be a secondary alcohol, and since there are 3 carbon atoms, it is propan-2-ol. Wait, it's propan-2-ol. Okay, wait. So guys, it must be a secondary alcohol such that the iodoform reaction can go and the oxidation reaction can work. Wait. Then now, friends, please, for the sake of time constraint, because I want all of people to have access to this video now before you go to the exam hall, we'll just name 2 of the in fact just 1 of the isomers. Okay, we'll name just one, and that is going to be, we have propanol and we have propan-2-ol, as I have it here on screen. Wait, that's now. Then so friends, which of the isomers corresponds to Z? So we'll just say they want us to give the corresponding, they want us to give the isomers of W, and we give a reason for our answer. So friends, to do that so well, we are going to have propan-2-ol. So that is actually the compound that is being formed. Okay, that's the compound that is actually being formed. That is what this is being formed. That is what the W actually stands for. Okay, that's what it actually stands for. The secondary alcohol. It cannot be carboxylic acid. It cannot be an aldehyde. Okay, it cannot be an aldehyde unless it is it has a methyl ketone group. But in this case, since it's an aldehyde, we expect what, guys, to be ethanol. Great. If it must give us a positive iodoform test. Good. So friends, that's what we have. And the question also the question is saying that we should give the isomers of that, and with a reason. All right. So friends, the reason is that W is a secondary alcohol, since the secondary alcohols, as you all know, can be oxidized to ketones. Good. And the ketone we are talking about here is what, guys? Is X. Great. You can try it out, then you see that it is a ketone and it's a secondary alcohol. Great. Then friends, the next question wants us to identify X, Y, and Z. So X, as you all know, is a ketone. This is the corresponding ketone. Then Y, guys, when this sodium gets reacted with this secondary alcohol we have here, what happens is that the sodium simply replaces one of the hydrogen that is attached to the hydroxide ion. So we are now going to have CH3 CHONACH3. Good. Then now, guys, the value of Z, now we are using red phosphorus. So red phosphorus is going to replace the OH we have here. So that's what we have: CH3 CHI CH3. Great. Thank you so much, friends, for watching. Keep watching the video because we are not done. Keep watching the video, keep watching it, guys, keep watching it. If you stop learning, guys, you definitely stop living. Great. Then, friends, the next part is saying that that we should give the reagents and reaction conditions for the conversion of W to X. Friends, to leave from W to X, all we need is simply we have manganese, we have the permanganate ion, or you have the potassium permanganate. Okay, I will just put permanganate ion. If you have potassium permanganate, you are on track. Wait. Then now, of course, we all know this guy is impotent without an acidic medium, so we have to acidify it with this H plus. This H plus might come from mineral acids such as you have concentrated sulfuric acid. Wait. Then, friends, the next part want us to give the conditions for formation of X. That's what we have given already. Then the last part is in that give the name and color for CH that. Wait. And friends, take it as a note that in place of potassium manganate, you can still use dichromate. Okay, you can use the dichromate ionist. You can use it so well, but you have to use the same medium, and you must heat for the reaction to take place. Keep in mind that permanganate is what a strong oxidation agent than potassium dichromate. Yeah, so we have, after using potassium dichromate, guys, we have to heat it to force the reaction to occur. Great. Then, friends, the next question simply wants us to give the color of CHI3. Great. As all know, guys, it's called iodoform. Great. That is the basis behind this our synthetic. That's a clue of it, the iodoform reaction. Great. Then now, guys, the next part is asking us to give the color of it. This is a direct question, guys. It's direct. It is simply yellow in color. Great. That's what we're supposed to give, guys. That's what we're supposed to give. Then now, friends, let's move on to the next slide to look at what we have. Then friends, the next part is want us to define what is meant by hybridization, and the second part we should give an example of an sp hybridized molecule. So, friends, as you can see here on my screen, hybridization is simply the mixing of atomic orbitals of similar energy level to generate new sets of orbitals called hybrid orbitals. Friends, I love this question. Why? Because the exam board now might decide here to ask you now to state the law. They can simply what they can do is that they can simply ask to define hybrid orbitals. No longer hybridization, guys, but hybrid orbitals. Keep in mind, hybrid orbitals have been formed from hybridization, right? Great. So just put it in the down below. Let me know your answer. Just put in the comment section down below. Let me know your answer. Friends, don't forget to like the video. Friends, please press the like button beneath the video. That goes a long way to motivate me to keep producing more and more content for you. Thank you very much, friends. So that is what we have. So let's move on to the next slide, friends, to see what we actually have there. Great. Let's go. But maybe we should answer this part. The next part wants us to give an example of an XP hybridized molecule, right? In such a case, guys, all you should be thinking about is simply the alks, okay? Simply the alkyne groups, not the alkyl groups, sorry, the alkyne groups, because the alkene groups, in fact all of them, guys, will give you an sp3 hybridized orbital, right? But for the alkene, guys, some will sp3, others will give you sp2. Good. Then now for the alkynes, now just ethene can give you an sp hybridized orbital, okay? Just ethene, because ethene has just 2 carbon atoms and you have 3 bonded pairs that have been linked to the atoms between ethene. Good. So 3 bonds. When you do analogy, guys, you see that ethene is the best answer for this question. Great. Let's move on to the next slide, guys. So, friends, the next one is saying that we should suggest chemical pairs to distinguish between the following pairs of compounds. This is methane, this is ethene, sorry, this is ethene, this is butanol. This is propanone. Wait, so now let's distinguish between these two guys. So as you all know, friends, you split them that into two separate test tubes containing both organic compounds. We are going to add small amount of bromine water, or we can add bromine in carbon tetrachloromethane in the dark. Why is it in the dark, guys? It's in the dark because if we put it in light for some long time, guys, we are going to have now but a free radical substitution reaction. Okay, we don't want those free radicals to interfere with it. We don't want free radicals to be produced. That's why we are carrying it out in the dark. Okay, in the dark. Wait, the condition is very important, guys, very, very important. So now with this, what then are going to be our observations, guys? We'll simply see that the reddish brown color of bromine is decolorized, and the test tube containing we have CH2, CH2, but not for that containing CH3. Wait, that's where you can distinguish which one is which. Awesome, guys. Then the next one is between propanol and propanone. So for in such a case now, guys, we are simply going to use the silver mirror test. Okay, into two separate test tubes as we are going to add small amounts of silver nitrate. That's ammoniacal silver nitrate, to be specific, ammoniacal silver nitrate, and we heat it, guys, and we heat it. Very important, we heat. What will be our observations, guys? We are definitely just going to see the test tube containing propanol, guys, the silver mirror which coats the walls of the test tube, but no observable change for the CH3COCH3. Great. Okay, because there's a silver mirror that coats the walls of the test tube. Great. Then, friends, the D part. Now we are done with the A part. The D part is saying that we should state the reagents and reaction conditions for the following conversions. We have this phenylamine to benzene diazonium salt. Wait, so in such a case, guys, friends, permit me to write the answer here. Okay, please permit me to write the answer here. So the reagent in which we are going to use nitrous, that's nitrous acid. Okay, nitrous acid, and this guy is simply being generated and used in situ. Great. Then, friends, the reaction condition we are going to have now is now going to be at a temperature that is less than 5 degrees Celsius, because at a temperature above 5 degrees Celsius, this our compound here is not stable. But we have it at less than 5 degrees Celsius. So, friends, thank you very much for watching the video, friends. Thank you so much, friends. Thank you so much for watching the video. Thank you so much, and don't forget to subscribe to the channel, guys. If you love the video, like the video, friends. It goes a long way to motivate me, and share that with your friends so they can have access to content like this before the exam time comes and they go into write. Thank you very much, guys, and have a blessed day, and good luck as you write your exams. Stay safe, guys, and I'll see you in my next video.